Alright, so this is reading assignment for next week, chapter 3, which is focused on thermal oxidation of silicon. And as we discussed last time, oxidation of silicon is the most, probably the fundamental feature that has made silicon the substrate of choice for semiconductor devices. And part of the reason was that it's grown easily and it has very different properties than silicon. So essentially we use it as an insulating material. We use it more importantly for the gate oxide, which is insulator used between the channel of transistor and the electrode of the gate. I'll go through a little bit more on the transistor today because I gather not all are on same page on what is. We know resistor, we know capacitor, but transistor is a slightly more involved, and we need to know at least the component before we start talking how do we make it. So the oxide is what has it is done using a furnace where we control the temperature and where we control the content of oxygen. So we can bubble oxygen through water and do a process what we call wet oxidation, or we just supply oxygen with nitrogen. Right? So that's again, what is that process? Fundamentally, where do we see that process happening? Oxidation. When we see rust, right? So, but in this case, we are using it to change silicon into silicon dioxide, and we want to change it to achieve very controlled layer of silicon dioxide. Now, think about it. If I have silicon which is electrically active, and of course after doping, and I put silicon dioxide. Now, how do we approach silicon through silicon dioxide?
Etch.
Etch. What is etch?
Etch is you take off something chemically.
So removal of certain material, right? But so it's like I have a whole surface which is covered of silicon dioxide, and I have silicon beneath. So of course there will be silicon dioxide from both sides. So I have to remove silicon dioxide from precisely known places, so I can approach silicon below that. If I need to make electrical connection, how would I approach silicon? So say I make an opening by what Bo said, etching. Now I need to approach the silicon. How do I do that?
You can use photolithography.
Use metal, and then of course photolithography is something which I will do to define this pattern also before I etch.
Deposition, right?
So we'll deposit some metal, right? So we'll deposit metal which will go everywhere. And then I will do another lithography, make a design again on the surface, and I will remove metal from everywhere. And this will give me a contact with silicon. I've skipped many parts, many steps in between, but we'll see how. But it's a general idea that why do we want to do oxidation? And how do we use silicon dioxide? So we use silicon dioxide. Now, when I say etch requires two things: selectivity and sensitivity. What does that mean? So many times we buy jewelry, right? So even men buy jewelry for somebody maybe. So a lot of jewelry has gold coated on it, right? What do they call it? It's a
Electroplate.
electroplating. So there is a layer of gold on top of maybe silver, right? So there is a coating of different material on top. Why do we put gold on other materials. What is good about gold? Why number? Okay, let's think why gold is expensive.
It's pretty.
It's pretty. Okay.
No, it doesn't oxidize easily.
It's a noble material. It's a noble metal, right? What is a noble metal? Yes, this is high school chemistry. What is a noble metal? Doesn't react, right? So it doesn't get degraded. It can stay whatever gram we buy for years. It will stay that same gram. It wouldn't get corroded. Even if you do the dishes, it doesn't react. So it's a noble metal. So we coat that thing with a noble metal, which basically safeguards whatever is below. Same is the reason we want to do silicon dioxide. Number one was electrically we want to have a material which is insulating. Other is we want to put a protective layer on top which doesn't result into further oxidation of silica. So it's a passivation layer. It's like painting a metal thing with a paint which doesn't let corrosion happen, which doesn't let rust happen. So it's a oxide is done to isolate, electrically isolate part and to passivate the substrate, to cover everything so no more reaction occurs with anything else. And why we are worried? Because we have to expose this wafer, this chip, to subsequent reactions, to do some different things, to deposit metal, to remove metal, so we have to have something. Same is achievable with silicon nitride by putting a nitride layer, by depositing a nitride layer. So I just said depositing a nitride layer. You would seldom hear growing a nitride layer. Why is that? So we discussed this growth versus deposition last time. We can grow or deposit silicon dioxide, but we can only deposit silicon nitride. What does that mean? What does that
We are
mean?
adding silicon oxide.
So we can do some chemical reaction and convert silicon into silicon dioxide, but we cannot do a reaction, easy or straightforward reaction to convert silicon into silicon nitride. So what we do essentially, we always deposit silicon nitride. So silicon nitride again serves the same purpose. It's insulator, and it has insulator means it's electrically different, and it can have passivation effect, which means it covers everything that's below and doesn't let further reactions.
Now, why is it difficult to grow?
What?
Why is silicon nitride difficult?
It's relatively easy to grow silicon dioxide. So yeah, this is an interesting question. Why don't we grow silicon dioxide, silicon nitride than silicon dioxide? As a chip manufacturer, and we'll see who are those, I want to save money. I want to have a process which is fast, rapid, quick, because that saves me the cost per die.
And see, it's not that we couldn't, we just don't want to.
So we have something which serves the purpose. Why do we want to do that with something else?
I have a question. How can I make sure that my silicon dioxide layer is uniform?
Uniform.
What does
We will look at that once you read the chapter. Once we get through this oxide part, we'll do all that. How do we ensure that? And it's one of the fundamental requirements: uniformity of thickness of any layer that you put, not or grow, not just silicon dioxide. All right. So this is something from 1957. Essentially, till today, we are using the same principle on many places, same apparatus. We have furnace, which is made of quartz. And quartz is, what is quartz?
Sand.
Sand,
As a big crystal.
big crystal, and it's glass. Essentially, it's glass, right? So it can withstand high temperature. And we load wafers in the furnace. We these are heating coils. If we pump in oxygen, which may be with water vapor or maybe just with nitrogen, and we let the reaction happen for a certain time. And after that time, we take it out and we know we got the desired thickness of oxide grown on silicon. So, and then we put copper as well. So this shows a magnified image of a multi-layered device. So it has 6 layers. So we are not just talking about a single layer of devices like I would do. For industry, is that many more layers. This is from '97 where they were making 6-level dies. So there were devices on every level. So, and this is 130 nanometer product, which shows a process called Damascene. We'll look at that. So the idea is that these are all layers of devices, and then there are wires which are running horizontal. There are wires which are running vertical.
On the same die, they got 6 layers.
Yeah. These are old devices. Now we have many more layers. But we'll get into that also. How do we interconnect different layers? Right? But we will not be making these. We will be making a single layer in the lab. Because all of you have heard Moore's law. Right? Anybody who has never heard Moore's law? The word Moore's law. Okay. So generally it's used in many different shapes, but the exact words were that it was a forecast for 10 years that there will be 65,000 components in a single silicon chip, which roughly translates to doubling after every 18 months. So this is the growth, and now we are somewhere where we have millions of devices on a substrate. There is something what we use to define what kind of technology we are using. When I say technology, translates to it's depicted in terms of nanometers. So 45 nanometer technology, 65 nanometer, or 22 nanometer. When somebody says we are at 22 nanometer node, but it means that the industry or the production has the capability of producing 22 nanometer channel. Channel is something which defines how far our source and drain. So I wanted to touch this. We'll keep on discussing this as we go along, but wanted to share. So this is a final FET product, MOSFET product. So essentially it has a few basic parts. There's source, of course, so it's written there. So we have source, we have drain, and we have gate, and this part is where the channel is formed. So the length of this guy is what is considered to define the channel, the node. So how long is the channel that is being used? And why is this parameter important? Because we can scale everything down. Ultimately, it's this channel that's going to result into the gating effect. What was gating effect? Gating is just like a gate. What does a gate do? What does a door do?
Let things pass.
Let people pass or stop them, right? So what does gate do here?
Controls the channel.
Controls the channel. And what does gate do? When you say control the channel, what happens by controlling the channel?
Blocks the current.
Blocks the transport of charge, right? So we can control the charge flow from source to drain by controlling the bias on the gate. So here, whatever voltage we provide. Okay, now look at this device and tell me what kind of voltage do we have to apply on gate to create the channel? What kind of bias do we have to apply on the gate to create the channel? Positive. So that will result into what's going to happen in this area when we apply positive voltage? Say it again. N channel will be formed. So negative charge carriers will accumulate in that region because of attraction of positive charge. They're spread around, so they will accumulate. But it's a p-type device, so those charge carriers, which is electron in this case, are they minority carriers or majority carriers? But its substrate is, the bulk is p-type, right? So they're minority carriers. There are few. It's a p-type material, which means there are much more holes available, but there are electrons available. So we attract those few electrons, in this case electrons, to come close to that surface. It's a cross-sectional view of the device, but it's actually a three-dimensional device, right? So it's a square plate where we are applying the gate voltage. We are accumulating all the charges to come together. Once they come together, they create a train of charge. So we can now have charge transfer from source to drain. So, but to get there, we have to have all these materials come together: silicon dioxide, beta, P plus material, aluminum, oxide, right? So our goal is not to study device physics, but to see how do we make this whole gigantic substrate, the device structure and all these parts.
So I'll expose some ignorance by asking this question, but is this...
This was all unnecessary. Ignorance. Okay.
Is this what you would call an NPN transistor, or are those a different kind of device altogether?
Yeah. Right?
It is an NPN.
It's, yeah, MOSFETs are N MOSFET or P MOSFET.
I see.
Yeah. So NPN is two diodes back to back. So, but essentially, you have to have a gate to get the transistor effect out of that. Yeah, that's how functionally in the blocks or with high level device point of view, yeah, that's how we depict it. But actually, this is what physically we make it. This is how we make it. So we have to now see all these steps. How do we make this semiconductor material p-type? How do we make some parts to be p plus, which means it's much more doped to be p-type in this region. But how do we control? Just it happens to certain depth. How do we make this n-type material within that bulk? How do we make this specific shape of aluminum? What is this thin oxide? This is all what we have to, what we are aiming to learn and to do it, to do some part of it. So this is something which is using hafnium-based high-K metal gate transistor. When you say gate transistor, which means they are using, instead of silicon dioxide here, they're using some other material which has high K, which is called dielectric constant. It has high dielectric constant, and we'll see reasons why do you want to do that. Right? Any questions on this simple transistor diagram? Right. So these are real pictures, real cross sections where we have 35 nanometer memory device. And it's the channel size that defines how wide is that device, and that defines the node. And again, this is 45 nanometer node device, so you have source, drain, and you have high K gate insulator instead of silicon, and there is That's where we get the gating effect. This shows that how small can we make the oxide. We can go down to a few nanometers, which is 2 to 3 atom thick layers of oxide as well.
The channel length that you talk about, the 45 nanometer, is it the effective channel length or the actual channel?
Yeah, so there's a formula how do we get from actual to the node length. But
So
generally
this refers to the effective channel.
to the effective channel length. Yeah. So and why effective we'll see, because there are many things we have to do to. There are issues when we make channel too short. They're called short channel effects. It's a specific term. So we have to do some things to get rid of short channel effects, which results into the physical length to be different than the length that we use to call it a node. Right? So this is to show that when you say uniformity of oxide thickness, so this is a few atom thick oxide, and it has to be precisely that. It has to be uniformly that thickness all over the device. This is just one transistor, and we have billions of transistors in one die, right? One chip. And then on a wafer, we have again thousands of those dies. And what's a wafer? Probably should bring it next time. So wafer is in labs, or what you will be using will be a 2-inch wafer. So it's a circular disc of silicon which is 2 inch in diameter. We use 4-inch wafers also. Industry uses 8-inch wafers, 12-inch wafers, and now they're using 16-inch wafer. So it's a big plate of silicon, 500 micron thick, and we have to make devices all over it. So that's the kind of uniformity we need over the whole substrate, a few nanometers. So what defines the node? There is a consortium called ITRS, which is companies, industry, academia, so there are different partners to this who define the roadmap. And there's an association called SIS, Semiconductor Industrial Alliance or something. So they define for next few years. I think they go to 10 years advance, and they define where we should be. So they, if you look at this website, I have some plots here from their website. So they define where the industry should be. Some of those projections are very, very like advanced or far ahead of current technology. But since they define their milestones, so industry pushes to get there. And so far, we've been catching up. And the goal is always to make devices smaller, faster, and cheaper chips. Now, we are pushing this device size down, which essentially results into higher density of devices, right? So we can cram many more devices in that same size as 10 years. But there's this trade-off. What is the biggest trade-off of pushing too many devices in a small space? Heat, right? So with heat translates into how much power motherboard, so to speak, consumes, and how fast can we transfer that heat away, right? Failure, there's much more failure. So instead of pushing in consumer electronics, pushing device sizes further down, we have found another way, that is using multiple cores, right? Quad core, right? So multiple cores. So we, instead of making one processor much faster, much smaller, we can put many in parallel to each other. And we'll see specific reasons for that. So you can, through their why that trade-off, that pushing one device to be even smaller and faster, we can use multiple cores. So what are main types of devices that we use? Memory processors, commodity integrated circuits and system on chip. We know memories and microprocessors, right? What are examples of commodity ICs and complex system on chips? We don't see them too often because most of those are for specialized users, military grade, for example, or used for what you call PLGs, which are dedicated for carry out certain functions in industry. So we don't see them in consumer electronics. So they are also major focus of the industry. So they keep on updating their roadmap, and which brings tables and collections from previous one and the previous year, which brings the latest information from the whole industry. So these are some of the numbers from some of the what you call metrics for different parts they have. It's from last year, so they have test equipment, RF devices, which is used in wireless, emerging devices, numbers on lithography, interconnects, integration. So these are all different parts of the industry. And as a process engineer, we may focus on one part of it. If I'm a lithography specialist, I have to know what are the issues with lithography. But ITRS puts up all those information out there. And again, this is from 2 years ago. I think they have a new one out there. So it just shows that the growth of industry, so it has an upward trend throughout the years, billions of dollars. It breaks down into different components. Many of the industry, much of the industry is focused on specialized uses. So major chunk of this revenue comes from military or for outer space applications, which we don't see in consumer electronics. All right, so what do we do? What all will we be covering to see the whole processing of fabrication? We'll be probably not doing bonding, but everything else is what you gotta do. So pattern transfer, again, so as a VLSI engineer, so you guys have to know that VLSI designers are distinctly separate from fabrication engineer, right? So VLSI is the art of placing down as many devices as you can, right? And testing them on computer and seeing that they would do exactly what the whole chip is supposed to do. But then that needs to be translated into a physical design where I have capacitors in the circuit, I have resistances, I have diodes, inverters, all those things. And that results into a functional map for a wafer, which may have multiple layers, multiple levels. Now, that's the same example that even if I just have to make a resistance, I may have to do doping into substrate for certain length and for certain width. So if I look it from top, I would have this region which is heavily doped, right? And I can make connection. So I can cover everything up, and I can make connection from here to here. So if I look it from top, I have this region which is open, and I can make metal connections with this guy. Right? So this would be a simple resistance. Why do we want to do it in substrate itself, why not use an external resistance? Can I use external resistor?
Size is better.
Not really.
Size.
Size?
How are you going to bond the million resistors?
Million resistors, right? So that's the basic idea of integrated circuit. Everything has to be integrated. Everything has to be within the bulk, right, next to each other. So this is something that gets translated from design of circuit into physical depiction, how it should be. What do? We make a thing called mask set. Masks are transparent slides or plates on which we make these design. Some parts of it are opaque, some of this are transparent. We use that to transfer our design onto our wafer. How do we do that? We coat this wafer with a thin layer of a material which is called photoresist. It's a liquid material. We coat the surface, we heat up the wafer, the liquid solidifies. So now we have this thin layer of material called photoresist. Why we call it photoresist? Because if we expose it to certain wavelength of light, it undergoes chemical changes, which makes it soluble at those parts or insoluble, depending on what time. So, simple analogy, an old analogy is that the reel on those old-fashioned cameras, what we used to call, if you pull that, if you open that reel, we used to say it has part here, but it was essentially, it was exposed with. I guess old enough to remember those reels on those cameras we used, right? What was speed of those reels?
100 to
100?
1600.
Yeah, so they
25
were,
to 1600.
so they were like 100. What other speeds they would come in?
100, 200, 400, 800.
400, 800, 1600, right? And they had to, if you remember that the camera was an isolated dark room, right? There was the only access of light in that camera was through, what do we call it? Front thing, shutter.
The aperture.
Aperture is
The lens.
how, yeah, aperture. So we had that shutter which was a door to that negative, right? So what did we have to do before we take that out? We had to roll it into another small dark room, which was that case of the negative, right? And then they would process it into specialized chamber where it would come out, undergo chemical treatment. And once it was treated with chemical, now the pattern was transferred onto the plastic sheet, right? So it makes sense? So that pattern was exposed when we would take the picture, but it was not yet transferred. It was transferred to only the coating which was on that plastic sheet. And once we do chemical treatment, that pattern was transferred into the plastic. And then that plastic, what we used to call negative, use it to do the same process, but now on a piece of paper. So that paper had that coating, which was light sensitive, and they would, I don't know if you know that, but they still show in movies where they have this dark room, which has light, bright light in there, and somebody is washing that sheet of paper, and suddenly the image comes out, right? So now, if it is dark room, why do we have a dark, bright light in there? Because that coating is insensitive to that wavelength, but it's sensitive to other wavelengths. So that paper is also something which is placed on somewhere, and negative was put in, and that coating was exposed to that light which comes through that negative. Exactly same process, same idea here. that we have this mask set made by a VLSI designer who has placed all the devices where they're supposed to go, and he has placed different layers of devices on different masks, because in one case I might have to make just just do this, what you call doping to make it electrically active. In another mask set, I will have to open these windows for electrical connection with the outside world. In another mask, I will then have to make this metal deposition. So define patterns where metal should go, right? So that mask set is, so when I say set, it's not just one of those, there are multiple of those, but we use them to transfer the pattern onto a photosensitive material which we have coated on a wafer. We expose it with UV light, specific wavelength, very, very precise wavelength, and we wash this coating in certain chemical called developer, interestingly, because that's exactly what it is doing, developing. So it removes that coating from exposed area or unexposed area, depending on whatever combination we use. But in any case, we will get the pattern transferred. Now, let me ask something. If I have this multiple mask, what is a major requirement for their alignment? So, think about that. In one mask, I make a line, right, and I dope it. Now I have to put, and then I cover everything with oxide. Now I have to open connection windows at the edges of that line. So what can you say about alignment for the second mask? Should it be exactly where the first line was?
Of course, I mean, you have to.
Right? Does it make sense? Okay. Stop me if it doesn't, because this is something we don't see every day. But once, if you understand this well, then the rest will be. So think about it. When I have to fix something into, and I have a bolt and I have a nut, they have to align to go in, right? So now, if this was my surface, and I did lithography and I exposed, I just did doping and I defined a resistor within the bulk. Now in next layer, I have to make connections. I have to get the lead out from edges, right? I don't want it to come from center. I don't want one lead to come from here, another from here, because that's not going to connect my resistor. So I have these two leads to be exactly coming from this place. So next mask, which is going to define the placement from a lead, has to be aligned very well with the first layer. So I used one mask to do this, that mask goes away, I do something and I put oxide, and now I use the second mask, but it has to be, now the mask is gone, but its pattern is there. So the second mask has to align with the pattern, so my leads can come out exactly from those two places. Does it make sense? So pattern transfer is a very in-depth thing. So we use lithography to do that. So lithography is, optical lithography is where we use light, ultraviolet light, to transfer the pattern on the surface. Once we do that, we may be doing implantation, put those, what you call, dopants. We might be doing etching to remove material from certain places. We may be doing deposition, putting material everywhere, and then maybe doing another lithography to define the pattern. We might be cleaning. Cleaning is very important because our devices are so small, they're even smaller than specks of dust. So if you have a dust particle land on your wafer and you keep on processing, we'll lose many of the devices, which is a matter of yield, right? If I don't get high yield of devices, they're going to fire me, right? So we need to keep it clean. While we do all that, we have to keep on looking how a process is occurring. It's called metrology. Metrology is looking at a process, maybe in situ. What is in situ? Have you guys ever heard in situ?
In place.
What does in situ mean? I remember it by in situation, during situation. So measuring it while it's happening. What does in situ mean? Measuring it while a process is happening. Right? How do we, give me example, where do we see a process while it's happening?
Most macroscopic things we see while they're
We
happening.
see macros everywhere. When we do a process, we want to get a feedback. Maybe it's a visual feedback. We want to see how things are progressing, right? Don't tell me guys haven't done any chemistry reactions. Litmus paper is used for that matter, right? So we keep on checking the pH. We get to pH also. We have lots of mystery. So we do check. What does pH tell us?
Or acidic or basic or something, yes.
So how acidic? So if we start with highly basic material and we expect it to neutralize and we still see this basic tendency, what does it tell us? Reaction is not done yet, right? Or many possibilities can be there. So you have to do metrology, maybe in situ or maybe end of the process. If it's so for in situ metrology, our sensing has to withstand whatever process parameter. Heat, if we do a process, maybe 1000 degrees centigrade, there are not many options available for in situ measurement, right? But there are. We can do something where we can maybe throw a laser and see reflection that can tell us how things are happening. Then we'll see what can be properties of laser that can change and tell us something. But metrology is very important, maybe in situ, maybe after. What would it directly impact? If we are not careful with the metrology, what would it directly impact? If I'm not careful in measuring the process outcomes, what happens to the whole batch of devices?
And we'll all be ruined, right?
May be ruined. What does that mean for the owner of the company?
File for bankruptcy.
Bankruptcy. So I'm not getting yield. The keyword yield. And I'm not cutting cost. I'm increasing cost. That's not what business are for. Business are paid to
So
make
what's
money.
a typical yield? I mean, how? I've always thought, you make something and it's made. I mean, what percentage do you actually lose? What's acceptable in the
So
industry?
yield, okay, now this is a very, what do you call it, closer or very narrow look we are taking. Yield includes many things, not just process yield, but the device, what you call mean time to failure yield, how long it can work, right? So we'll get to yield when we get to statistical process control. The later part, we'll look at that. What defines the yield of a whole process? So, and how do we control that? How do we mitigate the failure? That's a whole different game, right? Thermal process, of course, we know one thermal process so far. What is that?
Oxidation.
Oxidation, right? Done at high temperature. We'll see other thermal processes as we go on. So this is essentially a breakdown of what we're going to see. More precisely, these are the technical terms, terminologies. And as we progress, these terminologies will become easy because there's specific meanings of certain things, and that's my goal to make you comfortable with those. So, photolithography, transfer of design using optical wavelengths, right? Within that range. If you go above or below, it becomes different type of lithography. Oxidation we do mostly by thermal process. implantation or diffusion. Do I have diffusion? Yeah, diffusion are done to introduce impurities, right? Impurities for semiconductors are good if we know what we are using as impurity, right? We deposit material by PVD or CVD. They'll become easy as we go along. So you'll remember what is PVD or CVD. For me, it's, yeah, once you do it too long, you just consider it, we'll look at those closely. And then we remove some material, maybe the material which was already there, or maybe material that we have introduced, call it etching. And then we'll see that we have to polish before going to the next level. We have to get a clean slate before we get to the next level of devices. So we do that by CMP. There are non-CMP methods also. So essentially, summing it up, we start with we grow crystal. Do we see crystal in nature? Single crystalline materials, do we see them in nature?
All over the place.
All over the place. Okay, give me a few examples.
Salt, diamond.
Salt,
emerald.
Sand. Okay. So you guess partially wrong or partially right. Glass is half full. So yes, salt, sodium chloride is a crystal, but is it single crystalline material?
Depends on how big a crystal you have, right?
Right. So it depends on how big, maybe not, but each grain is probably crystalline.
You can get salt crystals about that big. They're rare.
So each. So the other thing was diamond. Diamond is a very fine example of a single crystalline material, but it occurs in nature, and because it's single crystalline material, it is expensive. So not many materials exist in single crystalline form in nature. If they do, they are rare. They are very expensive. So we have to make them. So sand has silica. Silicon we have to purify it. After purifying, we have to. It can still, if we solidify, it might result into what is called polycrystalline material, which has many crystalline substructures, but not a single crystalline material. Single crystalline material is something that has what is basic requirement for a crystalline material. Single crystalline material. Think about it. Structure repeats infinitely, right? Or to whatever size, whatever we are concerned with. If it doesn't, it means there is a defect. So electrically that will have implications. So silicon, what we use is single crystalline silicon for device components. But we do use polycrystalline silicon as well. So we get this big cylinder of single crystalline silicon and then chop it off. We'll look at how it is done.
So what's more common, polycrystalline or single crystalline? And what do we want to use?
Common where?
Industry or with what we're using?
Depends on what's used, but yeah, so polysilicon I can deposit in lab. I cannot make single crystalline silicon. That requires a whole, well, it requires a foundry where you can melt silicon and then make, well, we'll see how do we make ingot. It's called an ingot. So you have to have a pure seed of single crystalline material and you grow single crystalline silicon out of that.
Are the wafers single crystalline?
Yeah. That's the whole idea. So we get that wafer, which is a plate, 500 micron thick, and depends on so thickness and the what you call size. They all come custom made. So generally, 4-inch wafer we get for $20 a piece is 500 micron thick. And to give a perspective, how big is 500 micron?
Half a millimeter?
Half a millimeter. Yeah. So technically yes, but I wanted to give a relation with something which you can see. So a single human hair is 50 to 100 micron, right? So it's very thin, very fragile. And since it's single crystalline, it's brittle. So if you pressure it somewhere just slightly, it's going to break into billion pieces. That's exaggeration. If you generally it breaks into certain number of pieces. So if you put it right in the middle, it's going to break into 4 exact same triangles, sort of triangles. But so it's brittle. So we have that wafer, and then we do everything in the bulk or on top of the wafer. So before we do any process, first we have to define the areas where we have to do that process. So what we do is then use that mask set to do lithography. Just to get some idea, how much is a modern mask set cost for one type of, for one technology? What do you guess mask set would cost? This is a question which is not confined to you. Everybody has to give another answer.
You mean for a whole device, like an Intel
Mask
chip
set,
or something?
whole device, yes. So there's a bunch of plates, glass plates, right? But before you get there, people can place the devices and translate into physics. How much do you think would a mask set cost? $10,000 with all the design. Of course, you don't have to send it back to get the other design. So final mask set ready to go into production. How much would that cost? Give me a throw it.
Millions.
10 millions? Billions? Alright, anybody else? Yes? 10,000?
Millions.
Millions? It's about 3 to 5 million. So, but that's that device, but it has to be come before it gets to the mask stage. Rigorous testing that has to be done.
Now, is that the cost of making the physical mask, or is that the cost of design plus
Making
the
the physical
mask?
mask is a very simple process. E-beam writing will do the writing.
Okay, so this is like how much man hours you
Yes, so
spend.
there are bunch of VLSI designers sitting, and they have to
Yeah.
cram all those devices, and they have to define where interconnect is coming, where a via is coming, which is vertical, and where a connection is going, which is horizontal. And so all that, so straight capacitances and spacing between the, so it's a whole lot of, I can't even enumerate because that's a whole specialty how you do that.
The mask set, when they design the thing, do they even include the parasitics of the packaging, or that comes
Yeah,
later?
that all is part of the mask set, the mask design. Right? So, but then once, now they have to know the constraints of the fabrication also. So they have to know how small of lithography can be done reproducibly with reasonable yield. So they have to know that, do that design. So it's a big team that comes up with that.
So, how many masks do you end up with? Like for an Intel modern processor, what's the order of magnitude?
I think that we have it somewhere. I think that close to 30 masks, close to 30 lithographies that have to be done. I have it somewhere, I think. So it has to, before we get the whole, it has to undergo like about 30 of those. So in every lithography requires the previous, okay. So the design of the process, which is called, it was there on how do we integrate the whole process, has to be optimized. If I put a simple example, if I put a metal on the wafer, I put metal already to make maybe interconnect. Now, can I do 1,000 degrees centigrade oxidation? Think about it. No, because metal will vaporize, right? So it has to be the whole process has to be optimized, streamlined to know which can come after what, right? But yes, if I have metal, I can do PECVD, plasma enhanced CVD, to deposit oxide. I cannot grow oxide then, but I can deposit oxide.
Do they usually end up doing several iterations of these, or is it design and manufacture that refine?
No, I think that's the whole process. That cost goes into all that iterations as well. But
Because in the software world, we iterate ad nauseum until we get to something usable. Is it like that in mass design, IC design, or is
I
it
think
more?
there are many things which are very well known. For example, temperature. What's the budget, thermal budget? After undergoing one process, what is the thermal budget of that batch? Which would tell us how much high we can take it into temperature. So there are many basic things which are already known. So yes, for the next generation devices, they are already testing things, breaking things, looking at things, how do they come out. Even after modeling, we have to do it. Yes, you're right. There are several iterations going on into subcomponents, not the whole process. Yeah. So there are people who are coming up with different, maybe lithography techniques, so they can be phased into the main mask design process.
So the recipes generally just work
Rep-
once they're known.
Yeah, once the parameters are nailed down, those are established recipes. Then we don't touch them, we just do them, right? But there's an interesting side note to it, that whenever, if I'm a process engineer, I know how all of these things happen. But when I go into a fab, I have to know my machine, which means I have to run several characterization runs to know the behavior of machine. So I have to do it myself to see, okay, the paper says for 10-minute oxidation I should get this amount of oxide, right? Okay, now I'll do it myself and see what do I get. So I have to characterize the equipment myself, the process, before you do it on master wafer or master batch, right? So all those steps have to be characterized. So once you do lithography, then we might be doing doping, we might be doing etching, we might be doing whatever. So after we do one step, we keep on going to next. So until we do all the masks and we are done, and then we go to the next level where we have the whole wafer ready. Now we dice it. Dicing is cutting it into small pieces, making dies out of the whole thing, and then goes into packaging. Packaging is something which we will not do. We will look at some aspects which may be important for front-end integration, but we will not go into the details of packaging. Right? So, something which you will hear from me alternatively. So I may call it wafer or die, but I would essentially mean a substrate. Substrate is another word of same thing, that something that we are using to build up things on. So wafer or slice is single crystal, a block, very thin plate chopped off of this big cylindrical ingot. It's called wafer. Unit process or module is single processing step. So oxidation is a module, or oxidation is a unit process. Right? So you hear these interchangeably. Module, separate unit processes strung together build a structure. Now shallow trench, so we'll see all these things closely, but when I say shallow trench, it entails oxidation, and then lithography, then etching of oxide, and etching of silicon, then filling with silicon dioxide. So just trenching would essentially mean that a bunch of processes that go into making that. That will be another goal, that you guys will be comfortable in knowing many of these modules. When I say via, you would be readily clear what are steps that may go into making a via. So we'll go through we'll do this practice over and over with many things. Polygate again is using a polycrystalline material to act as an electrode. Heavily doped silicon, polysilicon is used as a metal, almost like a metal. So use it for gating. Spacer again, putting some object. So many things which we'll see, they essentially are composed of a number of steps that go into them. Device is an electrically active component. So bunch of things come together and make a device. So that should, if you remember those electronics block diagrams where we had this, we show this diode and we show this resistance and we show, okay, this is input and this is output, this is amplifying or unit output. Remember those? So we have those bunch of components. That's a device. Right? So in that case, what we show is maybe we do it on breadboard, we measure the output and input. Here we are making it all into substrate. That's why it's integrated. So that bunch of things is called a device. So when I say MOSFET or transistor, I'm talking about a device. Not just this source, drain, and gate, but associated resistances. But generally, we just take that source, drain, and the picture which I showed. So device also will be used in many levels. Circuit, the devices, they come together, build a circuit. Die is a single standalone piece that comes out at the end from that whole wafer, and process flow is the sequence of steps. So if you don't quite get what I mean by certain terminology in certain context, ask, so that we can go over what are other ways how you can define the same thing. Right?
So, Dr. I have a question. When you use ICs, you usually end up putting capacitors and resistors, etc., around them. Is that because you want some form of external control, or is that because some resistors and capacitors are just too difficult to build into devices?
So they're probably not too difficult, but to be flexibility, we don't put them on the IC itself. So that same IC can be now used for flexible ranges of resistances. So you don't want to hard code it, so to speak, right? So
Makes sense.
same thing what we do in software, we don't, many things we don't want to hard code, we want to leave it for the user input. Same is the case for that. So, right? Make sense?
Makes sense.
Right. So this is what all goes into the mask design. Right? For our case, we will not go into what are all things that go with, but we'll see. We'll start from wafer fabrication. So, but in design, we have an architecture, logic that comes together and we make a plan, right? Where we want to verify output of a circuit, of a device, and then of the whole circuit. And what those VLSI designers do, a bunch of things, schematics, vectors, design, and then they define a layout. So, and that layout is then verified. So when they do that layout, then they have to know all the constraints or limitations of fabrication, lithography and oxidation and etching. So all those things need to be known at this part. So when those are verified, they define the layout, how practically it should look like, where should be maybe a resistance relative to a transistor, where should be a source, a drain, gate, all that. So once that is verified, they result into what you call mask or reticle. Same thing, slight difference between mask and reticle. We'll look at that. What is a reticle, what is a mask? But we generally call these things mask. So this mask is a physical representation of this layout, which was on the computer screen. So now they have made something which physically is transferred to a transparent plate, quartz plate. And that is what we then take to transfer design onto the wafer. So wafer fabrication is, the circle is, red circle is essentially what we'll be spending next 16 weeks on. And then once you get it, then we test, we characterize it, goes into packaging. So what happens in that red circle? You get that wafer. So this guy shows molten silicon, and we'll look at this guy also, how it is done. Molten silicon, and this is what we call a seed. This thin thing is called a seed. So I have this fine, thin, pen-like structure, which is crystalline, single crystalline material. And I dip it into a molten cubic. It's called, generally we call crucibles. Crucible is a dish, just withstand high temperature. It's filled with molten pure silicon. I dip it and I draw it back. Once I draw it, silicon atoms, they're gonna get cold, they're gonna get solidified. But during this process, they're gonna follow the pattern of this crystal of my seed. Right? Once I draw it out, I draw a big cylinder with it. The size of cylinder depends on how fast I draw, right? But that, what you call ingot, the cylinder of silicon is now single crystalline, following the structure of my seed. So once you get that out, it's a cylinder, we polish it, we bring it to the size, cut it from a side. We put sort of at a scratch, we flatten out some part of it. That thing is called a flat, we call as a term. That flat tells us the orientation of silicon. Hang up, stay here with me, don't get too worried about orientation, we'll talk about orientation. For a crystal, if it's a pure cube, we have an atom at every edge of that crystal cell. Right? So look at, if you think about it, if I have this is essentially my our definition of crystal, right? So this repeats on all sides. And there's a repetition of this structure in all directions. So this one guy is called a cell, unit cell, right? So depending on that, we create what we call flags, tell you the orientation of silicon. I will see why is that important, but for now just focus on, we make those wafers, we put them in furnace, we oxidize them, we may incorporate impurities, of course. Semiconductor has to be doped to become electrically active. And we then use mass to pattern. We may etch, we may deposit, we do the whole process few times, and then we end up with this wafer which has distinct number of dies, and then we test the devices of those dies. Right? Makes sense? And then from there it goes into, we break each one out. It can be, we dice it like this, so each square rectangle has a number of dies, which go into this die, as we saw in the bigger one, those black things. We make connections, we package it, and it's ready to ship out. Right? So this is showing this dicing saw. The wafer is here, and this is a blade which has diamond coating at the tip, moves at really thousands of RPMs, cuts through silicon. It's called dicing saw. Right? So this thing goes now into a circuit board. Right? So if you look at, if you open up a microprocessor, you find something like this where some just very small part of the whole package is where the actual silicon is. Rest is all connections and heat sinks, right? So now this one of this, there may be many devices, source, gate, bipolar transistor, right? Any questions? Let's probably stop here. I wanted to get into semiconductor materials. Azure is a GPA, so he'll be taking care of the labs and most of the outside of the class issues, homeworks and assignments and everything. So he's also part of our Blackboard. He can access him through there. I had his email address on slides last week, on Tuesday. So we'll be posting his office hours also, where you can see him in Naroka Annex, which is cubicle. Questions? Is it time? Is that what?